the last lesson, we were using our normal antiderivative techniques to take definite integrals. We can also take integrals in those situations where we have to use u substitution to do the antiderivative. There's just one additional change that we need to go over. When doing u substitution, you do not have to substitute u back in at the end if and only if you change the bounds of integration when you do the initial substitution. The upper bound remains on top, and the lower bound on the bottom, regardless of which is larger. Having different rules for when we're doing integrals versus when we were doing the antiderivatives can be kind of confusing. So let's make a little chart just of the differences. So here's what we were doing in the past. So this is without numbers, antiderivative of f of x dx. And this is with numbers from a to b, f of x dx. And remember from yesterday, here we must have, here we, plus c, here we don't use. Over here we substitute u back in. At the end, here we change bounds when we substitute u. At first, but don't substitute u back in at the end. So let's do a couple of example problems. Let's do the antiderivative from 0 to 1 of e to the 2x plus 2 dx. And we see that this is a box function right here. So our u is going to be what's in the box. Take our derivative and manipulate it to get dx by itself. Now, when we do this substitution to change the x into the u, our numbers that we plug in are going to change. Because if we just write this, if we have 0 and 1 here still, plugging 0 in here is not the same thing as plugging 0 in for x here. They come out being very, very different numbers. So what we always have to do, this is probably the trickiest part to remember, whenever we use u substitution, we also have to change the bounds. So whatever the upper bound is, that's going to stay on top. So we're going to have u of 1, that's u of, not u times. And what we're going to do is we're just going to use this u function, put 1 in for x. That gives us 4. So 4 is going to go on top. Then we're also going to do u of 0, so we're going to put 0 in, giving us 2. So we're going to have 2 on the bottom. So make sure here that you change those bounds. The nice thing about this is that now when we keep doing this, so let's say this 1/2 is out in front. Now when we take the antiderivative, that's just e to the u, 1/2. And because we've changed those bounds, we can just leave those numbers right there like that. It's a little bit of a shortcut, because normally what we would have to do is we'd have to put the 2x plus 2 back in here, and then we would put these original x's back in. So we'd have to do all these calculations down here at this step. If we just change the bounds of u, we don't have to worry about it. So let's work with it that way. Notice this 1/2 is outside this part where we're doing the bounds. If we had left this 1/2 inside, we would just have a 1/2 times this term, and then a 1/2 times this term over here, which is the same as if we've factored out a 1/2. So what we can do is we can just leave this 1/2 out here. We're just going to do all of our substituting of bounds inside. So e to the 4th minus e squared and that can't really be simplified, except, I mean, this is all over 1, so we could write this as e to the 4th minus e squared over 2. When you're using u substitution, it is incredibly important to check your work. There are a lot of different places where you can make an error here. So let's do e to the e to the 2x plus 2, comma x, comma 0, comma 1. You could have made an error anywhere in recalculating the bounds, doing the u substitution. So it's very important to check that there, and then check and see if that's what we got for our answer. E to the 4th minus e squared divided by 2. They check out. There we go. And just 2 more examples and then we're all set. So for our second example, let's do the integral from -2 to 3 of x, negative x squared plus 4 to the 3rd dx. We see that we have a box function right here because of that power, and that when we take the derivative, this is going to be the same degree as that, so they'll cancel out, which is good. So we can let u equal negative x squared plus 4. The derivative, we bring down the 2, negative 2x, derivative of 4 is 0. So du over negative 2x equals dx. Now, because we're using u substitution, we have to change the bounds. Let's do our upper bound on top. U of 3, I put 3 in here, negative 3 squared plus 4. So that's going to give us 3 squared is 9, times negative is negative 1, plus 4 is negative 5. So when I'm rewriting this, that's going to be negative 5. Whatever's on top stays on top. Doesn't matter if it's positive or negative. For u of negative 2, we've got negative 2 squared plus 4. So negative 2 squared is 4, times the negative is negative 4. Negative 4 plus 4 is 0. So that's my lower bound. Notice this one is now smaller than this one. That's okay. Whatever was on top here stays on top here. Whatever was on the bottom stays on the bottom. Does not matter if it's larger or smaller. So let's see, this whole thing was u, so we have x times u to the 3rd times du over negative 2x That's good because those x's cancel out. We can bring that -2 outside. Now we can go ahead and take our antiderivative and write our bound. So that's u to the 4th over 4 from 0 to -5. So when we substitute that in, -1/2, -5 to the 4th over 4. Oops, I'm about to write plus there. I should not be writing plus, I should be writing minus. This is 0 to the 4th over 4. Notice these brackets are just functioning like normal brackets, like big parentheses. Once these bounds go away, we're all done with the substituting part. So now, when I simplify this further, 0 to the 4th is 0. 5 to the 4th, 5 times 5 squared is 25. Square that again, 625. Multiply that out, that's -625 over 8. Again, super important. Check it. Use the original equation. Okay. Yep, same thing. There we go. Our final problem is dealing with the lovely trigonometric functions. Integral from pi over 4 to pi over 2 of e to the cotangent of x over the sine squared x. That's dx. Well, we see a box function right here, so that's a good candidate for u. Again, you just got to know that the derivative of cotangent is negative cosecant squared of x. Now, we're going to want this negative cosecant squared and the sine squared x to cancel out, but they don't look the same right now. One of the key things that we have to remember is that cosecant is the same thing as 1 over sine. So if we have this, if we have negative cosecant squared x, that's the same thing as 1 over negative sine squared x. Now these are going to cancel out nicely. If I multiply both sides by negative sine squared x, multiply both sides by dx, I get that nice piece there. Now I have to make sure to change my bounds. So u of pi over 2. Well, all it is the cotangent of pi over 2. So let's go down here. Let's just figure out what that is. So I'm going to draw my axes. Pi over 2 is right there. Its coordinates are 0, 1. I know that the cotangent of x is 1 over the tangent of x. And tangent of x is y over x, so it's 1 over 0. Now this is a part that's a little bit strange to look at, because here we have division by 0 down here in this denominator. And typically we would say, oops, nope, can't do that, no log. But one of the things about cotangent of x is that while we think of it as 1 over tangent, it's the case that it is its own function. So in this case, one other way to look at this is that the cotangent of x, well, the tangent of x here is sine of x over cosine of x, meaning the y value over the x value. And The cotangent of x has its own definition, cosine x over sine x. Meaning that if we just use that definition here, what we're going to get is we're going to get 0 over 1. We're doing the cosine of the x-coordinate over the y-coordinate. Now, this is a little problematic mathematically because it looks like we've got division by 0 and we're flipping it over and we're applying our normal rules when we can't. But if we think of cotangent as having its own definition, then this step here isn't really coming into play. We're just going directly from here to there. Basically, cotangent is x over y, whereas tangent is y over x. So although this is a problematic step, if we think of it using the different definitions, it is okay for us to just say, okay, cotangent of x is 0. For pi over 4, at least we don't run into that. Triangle is 1, 1, root 2. So here we're fine. We can say cotangent is 1 over tangent. Tangent is opposite over adjacent. That's just equal to 1. So coming all the way over here again, this is the integral from 1 to 0. Remember, what's on the bottom stays on the bottom. And then u is cotangent of x, so e to the u over sine squared x. And then we have negative sine squared x du. These are going to cancel out. Okay. At this point, we can take the antiderivative. Whoops. Be careful of that. You're going to want to put the smaller one on the bottom. Whatever's on the bottom stays on the bottom, and right there. Notice if you had taken this negative and put it outside, you're still actually going to end up with the same answer, because you kind of distribute it back in at the end. So negative e to the 0 minus negative e to the first. Anything to the 0 power is 1. Negative minus a negative is positive e. So we have negative 1 plus e, or e minus 1 as our final answer. When we put that in, notice this is a little bit tricky simply because there is no cotangent button. We have sine, cosine, and tangent, but no cotangent. So we have to remember that cotangent is 1 over tangent. So we're going to do e to the 1 divided by tangent of x. We've already made sure our calculator is in radians, so that's okay. Okay, close parenthesis right there. Divided by, remember, sine squared x is the sine of x squared. Our variable is x. Our lower bound is pi divided by 4. Our upper bound is pi divided by 2. Oops. Looks like I lost a parenthesis somewhere. So there's a starting parenthesis, starting parenthesis. Okay, here's what happened. I need another parenthesis right here because this parenthesis closed off the x in the whatever tangent of x. But I have to cut another parenthesis closing the e to the power of subject. Okay, one parenthesis there, final parenthesis. Okay. And let's see if negative 1 plus e to the first power, whoops, same thing.